Ripple is infrastructure for global financial settlement. David Schwartz is the chief cryptographer for Ripple Labs. David, welcome to Software Engineering Daily.
Thanks. It's a pleasure to be here.
What is Ripple?
Well, Ripple was designed to take the distributed ledger, no central authority concept from Bitcoin and extend it to handle different kinds of assets. So it's a multi-currency, cross-currency payment network that's open. You can kind of think of it as a giant asset exchange marketplace. At Ripple Labs, we think the biggest use case is moving money between financial institutions, mostly because Ripple does this so much better than existing systems do.
And for listeners who want a higher level overview of Ripple's product, I did an interview with Greg Kidd several weeks ago, and this interview will focus on the engineering of Ripple. So for applications, higher level things, I recommend checking out that interview. So with that in mind, a good place to start is Ripple's consensus algorithm. This is at the core of the engineering behind Ripple. Consensus is a hallmark of distributed systems. Could you define consensus and explain why it is so important?
Well, consensus is essentially eventual agreement. And the reason that it's so important is because these systems face what we call the double spend problem, which means if a person has some kind of an electronic asset, they have to be able to send it to somebody. And if they try to send that same asset to two different people, we need to make sure that one of those succeeds and one of those fails. If you could actually send the same asset to two people, that would be a very useless system because assets could just multiply and there'd be no way to authenticate them. So what consensus means essentially is that we all have to eventually agree on who holds the assets and who they've transferred them to somehow.
This is Security Week on Software Engineering Daily, and eventually I'll ask some stuff about security, but I'd like to continue with some more explanation of the basics of Ripple. Could you explain a simple transaction end-to-end and describe how the consensus will proceed?
Sure. So a transaction starts with somebody who wants to perform a transaction for some reason. Maybe I want to send you some money. And so the first thing that I have to do is I have to form that into a specific structure so that it covers the details, who I am, who you are, what I'm transferring. And I produce that electronic transaction, and then I submit it to the network. And the first thing that happens is servers look at that to say, does that look basically valid? Does it look sane? And if it does, they relay it. And soon the whole network knows about the transaction. Then in the Ripple's consensus process, servers that are called validators, they're the servers that actually execute the consensus algorithm, will propose that that transaction be included in the next group of transactions. They then have an algorithm called avalanche, which essentially means you go with the majority. Once there's a supermajority agreement that that transaction should be processed in this block or this ledger, the transaction is processed. And then it produces final results, and then the validators all sign those final results and broadcast those validations. Once you see a supermajority of validators that are signing the same ledger, you know that it's been agreed on by the network and it's irrevocable. If that contains your transaction, you then know that the transaction was executed and you know its results. So for example, if I tried to create a double spend, let's say two transactions that send the same funds to two different places, what would happen is the validators would agree to process one of those transactions before the other, and whichever one was processed first would unfund the other, and so the second one would fail, and everybody would know that.
And I'd like to define a few other terms before we move into more detailed questions. What is a unique node list?
A unique node list is the list of validators that a particular server pays attention to. So in the consensus system, it's essentially agreement, but a malicious person could create thousands of servers if they wanted to, and they could all agree with themselves, and they could create the illusion of agreement. So what servers do is they pick a set that we call the unique node list of validators that they're going to pay attention to. And what they're looking for is essentially identities that they know are very unlikely to collude, that are unlikely to be controlled by the same entity.
Could you also define the term last closed ledger?
When the consensus process completes and a new ledger is built, that's called the last closed ledger. So if the consensus process closes a ledger, and the one that closed the most recently is the last closed ledger.
How does Ripple's consensus protocol differ from Bitcoin's consensus protocol?
So Bitcoin's consensus protocol uses proof of work or mining, which essentially means that people do mathematical work that they then sort of pile on top of the transactions. And the transactions with the most mathematical work piled on top of them are the ones that we consider authentic. Ripple uses a completely different mechanism where there's a network-wide agreement on each ledger. So rather than one person essentially building a block and then the rest of the network accepting it, there's full participation by the network in the generation of each ledger.
And does Ripple have a blockchain?
So it kind of comes down to how narrowly you want to define the term blockchain. Ripple has a chain of ledgers, which function somewhat analogously to Bitcoin's blockchain. So it's really just a matter of how narrowly you want to define the term. They're also secured by cryptographic hashes. They also have a sequence where one follows another. They also contain transactions, and it's by their inclusion in that chain that people know they're authentic. So they have a lot of similarities. It's really just a question of definition whether you want to call it a blockchain. Most people would not consider Ripple's chain of ledgers technically a blockchain.
I have a pretty broad definition of a blockchain. It tends to basically just be like a loose data structure description. But how would you define it? How do you define the term blockchain?
So I guess I also give it a fairly broad definition. I define a blockchain as essentially a chain of digital structures that each one points to the one before it. And each one essentially changes the state relative to the one before it. So if you imagine on Bitcoin, there's a bunch of Bitcoins that people hold, and then a new block sort of changes who holds some of those Bitcoins. And by that broad definition, Ripple would also be a blockchain technology.
You say that a blockchain fundamentally is used for consensus, or is it a more broad data structure that has applications beyond consensus?
Well, certainly the modern blockchains evolved because of the need to solve the consensus problem. So the reason that we use blockchains, if you imagine a central database operated by your bank, they may snapshot it one day just in case there's some auditing problems. They can see what happened yesterday, but they don't necessarily need to know the history in order to know the current state. They're perfectly happy just to store the current state. But because we need a consensus system where we have to agree on what happened, in order to agree on what happened, we all have to be able to tell whether changes are valid or not. And so in order to do that, we have to know more of the system's history. So the structure definitely grew out of the need to provide a distributed consensus.
Is a blockchain synonymous with the term Merkle tree?
Not quite. Merkle tree is kind of a broader term that covers data structures where data is referenced by hash. And the reason that Merkle trees are designed that way is that you can't be misled about what's in the rest of the data because everything is secured by its hash being included in something above it. And you get a tip hash that secures the entire data structure. That's also true of blockchains or ledger chains, but blockchains or ledger chains are just a little bit more specific in that they form a linear chain structure, whereas a Merkle tree typically would produce a less linear tree-like structure.
Explain the trade-offs between Ripple and a proof-of-work-based consensus like Bitcoin.
Well, so there are a lot of similarities. They're both distributed ledgers. They both have no central authority. They both use some sort of consensus process to reach eventual agreement on transactions. A couple of the big differences, one of them is sort of how you would handle an attack. So if you had like a malicious miner on Bitcoin that gathered a large amount of hashing power, it's not really clear what you would do about that. You could theoretically change the mining algorithm, but that would be something that would cause everybody who had invested in mining equipment to be extremely upset. In Ripple's consensus system, it's very clear what you do if you have malicious participants. You just stop listening to them because you have control over that. The other thing that I think is important to distinguish is that in Ripple, every validator participates in the decision of what transactions to include in every ledger, whereas in Bitcoin, one miner mines each block. And in a cross-currency system, if you had a proof-of-work-like system where somebody got to choose each block, the person who chose that block could construct that block in a malicious way. What they could do, for example, is let's say there are people willing to trade dollars for Bitcoins, and the exchange rate has changed a little bit so that there are some offers that are bad for the person who placed them. The person who mined the block could take all of those offers, and he could delete any transactions that tried to cancel those offers. And he could find payments. Let's say someone wanted to buy a Bitcoin and they were willing to spend up to $250, but they only had to spend $230. They could buy the Bitcoin for $230 and resell it to that person inside that same block for that higher price. So you couldn't build a sort of liquidity marketplace on top of a proof of work system without finding some way to address the problem that people would acquire mining power, not for transaction fees, not for mining rewards, but to be able to take advantage of the marketplace by things like front running and so on.
Does Bitcoin philosophically say we don't think that somebody's going to take over a majority of mining power and take control of the system because that would reduce the value of the currencies with the currency within the system? So in order to like take over that mining power, you're essentially devaluing the currency. Is that the argument that's often made in defense of Bitcoin?
Yeah, and I think the evidence shows that works pretty well. That the community has the ability to exert some pressure. A more dangerous scenario, and again, this is all just theoretical, is that there could be somebody who's acquiring a large amount of mining power sort of surreptitiously. They're either not mining right now or they're mining in many different pools, and then all of a sudden one day they're going to launch some sort of attack. To make that profitable, you would have to imagine that they have some way to benefit from harming Bitcoin that justifies the damage they would do to their own investment in mining. So it's kind of one of those movie plot scenarios that people don't particularly worry about. They're interesting to think about theoretically, but I certainly, wouldn't let it keep me up at night. And it proves that these systems are fairly robust, even when their security relies on sort of loose agreements among people.
But you still could, like you said, have some conceivable anarchist, that would destroy Bitcoin or actually have an incentive for it. So I do appreciate the Ripple model of things where there's more control over that sort of catastrophic behavior, as I understand it. So every distributed payment network faces the problems of correctness, agreement, and utility. Could you define these terms and explain why they are so fundamental?
Absolutely. And you also put them in precisely their order of importance. Correctness is absolutely priority one. If you imagine a system like Bitcoin or Ripple, you can't create funds out of nowhere. You can't spend the same funds twice. If you could do that, the system would be totally and completely useless. It would serve no purpose. And fortunately, that's the easiest one to get, because the way you get correctness is everybody enforces correctness rules. So even if even if the majority of Bitcoiners or Ripple servers did something that wasn't correct, you running your own piece of software would still enforce correctness rules and you would not be misled. So that's the most important, but also the easiest one to get. We get correctness by deterministic rules that everybody who runs the software knows and understands. Agreement means that eventually we have to agree on who holds an asset or who transferred an asset to who. That's a little bit more complicated because if I hold an asset, I can submit two perfectly correct requests to transfer that asset to two different people. So correctness will not get us agreement by itself. Agreement is what Bitcoin gets by proof of work. It's what Ripple gets by consensus. So it ensures that at some point, we know for sure that something has happened and that other people will agree that it happened, so we can rely on its results. Now, correctness and agreement could be perfectly maintained in a Bitcoin or Ripple system that processed no transactions at all, where assets never moved and nothing ever happened. Everything would be correct and everybody would agree that nothing happened, but it wouldn't be a useful system. So utility means essentially that we want the system to be able to process correct transactions and reach agreement on them at some sort of a reasonable rate. We don't want it to never process a transaction. One transaction a day wouldn't be much utility. So correctness is the most important. Without correctness, we have nothing. Agreement is the second most important thing, because without agreement, we can't rely on the results of transactions. But given that we don't sacrifice correctness and agreement, the point of the system is to provide as much utility as it can, to process transactions and do something useful.
I find it interesting that these three terms sound very familiar. I took a distributed systems class in college, and there were a lot of proofs around proving that your distributed system works as you think it does. And each of these proofs, you have to prove like these certain properties about the system that you're building. How direct has the extrapolation from academic distributed systems concepts to active implementations such as Ripple, like these real-world implementations, how direct has that extrapolation been?
Less than I would have expected. The practical algorithms seem to diverge very significantly from the sort of theoretical clean ones. The real world is a little bit messier than these clean algorithms. It just turns out that in the real world, there's all these other issues that you have to deal with that you don't have to deal with in an academic issue. Like a good example in Ripple would be Ripple has to deal with the fact that some validators might have very poor performance at least some of the time, and some validators might be very, very fast. And you don't want to be as fast as the fastest validator because then you would lose all of your protections against collusion. But you don't want to be as slow as the slowest validator, or you would have very, very poor utility. So you have these complex practical questions. You also often the theoretical algorithms, the algorithms that you'll see in the literature, will have an assumption like that there's some certain fixed limit that a message will never take more than some specific amount of time. And those types of assumptions don't fare very well in the real world. You want to sort of be adaptive. You want to look at what you're actually seeing. And so all of the ugly complexities from the real world have made these sort of nice, clean, elegant theoretical algorithms from computer science not translate as directly as you might think. Now, I'm not to say that research is not useful. If not for that type of research, we wouldn't understand how to build these practical systems at all. But it's kind of like the difference between, a theoretical analysis of a combustion engine and building a car. I mean, there's a huge gap between those two tasks. But you couldn't build a car if you didn't understand how a combustion engine works. So we need the theory, but the practice, there is a huge gulf between them.
My professor was actually in the Ripple paper. He was Alvisi. He was on the Fast Paxos paper, I think. Has there been an interesting feedback loop? Like, has the practical, in the wild, distributed systems experimentation of things like Ripple fed back into academia and made certain curiosities emerge?
I think so. I think we're seeing a lot. First of all, just generally, we're seeing a lot more academic interest in these types of distributed system, no central authority algorithms, just because people are starting to use them and they're starting to encounter these problems. But also, some of the real world requirements are filtering back into academia. So, for example, one of the reasons that you couldn't use something like Paxos or PBFT directly in Ripple is because those algorithms require all of the participants to agree on who the participants are before the system starts. That's a non-starter for Ripple. So now people are looking theoretically at systems like PBFT and Paxos and saying, well, what if we didn't require, agreement? How would that change the guarantees? How would that change the algorithm? And I think we'll get more, work in that area that will inform how we design future systems and perhaps how we improve systems like Ripple and Bitcoin. So there's definitely a feedback loop, and academia is definitely interested. Another thing that we desperately need academia for is security, and maybe I'm jumping the gun on what you're going to ask, but you can't just build something to be secure. You need academic people to look at it and analyze it and study it and come up with certain attack models and ways that it might fail and give you feedback on what you need to change. So we definitely need that loop to build systems that are secure.
Can you describe how that loop works in practice?
Well, in practice, an algorithm is first, like a high-level crypto algorithm is developed academically. It's studied for its security properties. And at some point, it reaches the state where we have enough confidence in its usefulness that we can actually use it in real systems. And that can take 20 or 30 years, especially if it's classified at some point in its history. But at that point, we start to use the algorithm. But when we use the algorithm, generally, it's not just an algorithm all by itself that does anything. Like RSA, one of the first symmetric crypto algorithms, by itself, it has all kinds of problems that would make it almost completely useless if you don't build it into a system. And so you build it with other parts, and then you sort of have to go back and say, okay, did I break it? Or did I use it in such a way that in the system it's safe? And then people start looking at how those systems are used academically, and then they come up with better ways to, like padding is a good example. Like you need secure padding for RSA to be secure. And at first, people just sort of made up padding algorithms that seemed good to them, and then academics looked at those and said, oh no, you're creating vulnerabilities in the way you do this, and so they designed better padding algorithms, which then filtered their way back down into practice. And it's definitely a feedback loop. They generally start in academia, then they get used in practice. Then academics start to look at how they work in practice and come up with improvements. And that's definitely how we build products that are progressively more and more secure.
In this ping pong between academia and industry, what are some best practices for thinking about security in a distributed system, whether you're on the applied side, such as yourself, or you're on the completely academic side?
Don't try to do too much is definitely a big one. Don't create for the sake of creating. Don't try to be different for the sake of being different. And don't try too hard to anticipate the future, because the things that we have today and that we use the most today are the best studied, because it would be the most interesting if we found security flaws. If you try to grab the newest whiz-bang thing, even if there's an argument that it's in some sense better or even more secure, you take the risk that it hasn't been sufficiently studied. So be very conservative. Be very humble. Get other people to look over what you do, and don't assume you know something that you don't. Because a lot of people, seem to think that they took one course in security and they're experts, and nobody is enough of an expert that they can do everything by themselves. You will have blind spots. Everybody has blind spots, and it takes people with different types of thought to figure out what attacks there might be or where there might be vulnerabilities. It's very, very difficult to build these types of secure systems. I mean, Satoshi Nakamoto, whoever he or they are, made tremendous strides. It's kind of astonishing to have all that happen in one step, really.
When you were designing Ripple, or helping to design it, were there any rough drafts of the protocol that you realized were insecure and that you had to refactor?
Not in the core sort of correctness portion of it, because those rules are fairly simple. A transaction has to be signed by a cryptographic identity. You check the signature. At the design level, correctness is not that difficult. At the agreement level, yes, we experimented with many, many different models of consensus. So we were the first people trying to work on a consensus algorithm where the participants were sort of loosely agreed on, not strictly agreed on, where there was just overlap in the agreement of the participants, not using proof of work. And so we tried a lot of different ways to do that. We originally had a much slower algorithm, and we tried faster algorithms, and we had to do a lot of simulation to see what would actually work under different types of failure cases, like networks being partitioned and so on. And that part of it took an enormous amount of experimentation and work. When we first started, we didn't even know if it was possible, because nobody had built, proof of work was the only way to reach consensus without a central authority, other than the algorithms known in the literature that all required strict agreement on the participants. None of them could be done without a central authority. And we didn't even know if it would be possible. And if it was possible, we had no idea whether it would be good for anything, or whether it would have any real world usefulness. So we went back and forth trying many different types of designs to find ones that were resistant to the different types of attack models that we anticipated.
You mentioned network partitioning. Ripple is in some sense a distributed database. Does it fall under the same constraints as any other database in terms of cap requirements? Absolutely, yeah. In terms of safety liveness trade-offs and the cap problem, yes, all of those problems apply to systems like Bitcoin and certainly to Ripple. And you have to make decisions of how to handle those problems. One of the things that we did not do in Ripple ever is trade-off safety. That's a design decision that we've gotten some criticism for. Bitcoin does trade off safety. Like, for example, if the Bitcoin network were to split in half, both sides, you could see a transaction get 6 confirmations on both sides, and it could be 2 conflicting transactions. Now, it is very unlikely to happen in practice, but it's an example. And I'm not saying that that's not a rational trade-off to make, but it's an example of where you trade off safety in exchange for getting things like liveness. And you have to tolerate, if you have a partition in Ripple, what will happen is you just won't have a supermajority on either side. If you just chop off a very small piece, then it won't matter. But if you chop off a large enough piece, neither side of that will have a supermajority, and so the system will show no liveness. In other words, it won't confirm any transactions. One basic design principle that we adopted in Ripple very early is if reliable operation is not possible, don't pretend. Make it very clear that you're in a situation where reliable operation is not possible. And then it may require human beings to make some changes to restore the system to operation. But that's preferable, we thought, to having a system that told you that you could rely on some information that actually was unreliable.
It remains to be seen whether that was a good decision. I mean, I personally certainly still stand by it, but it'll be interesting to see as Ripple is more broadly adopted whether we do have liveness problems. I think we've made the right decision. I think the idea that if you're targeting the type of market we are, where we're targeting large transactions on the part of financial institutions, they need reliability, and the systems that we're competing against, the centralized systems, the closed systems, certainly can provide those guarantees. So we turned a lot of those knobs all the way in one direction. And we think we can make the system live despite that.
Was that preference for safety over liveness at all inspired by the classic Paxos algorithm? Because if I recall, the initial implementation of Paxos was basically, under worst case scenario, there is no liveness.
Right. Yeah, absolutely. We looked at algorithms like Paxos and PBFT. To see how you would start to do this without, because with the proof of work is completely different. But once you've given up on proof of work and you're working on it like a direct agreement, then the closest literature to look at would be things like Paxos and PBFT, and they do trade off liveness. They basically say if we can't guarantee that we have the correct results, then we want to definitively be able to tell people that and not give them results that would be misleading. Absolutely.
Do you think in these distributed value systems such as Ripple or Bitcoin, are we in a similar point in time where we were with classic distributed systems when the Paxos paper was published, and we're just going to continue to see these advancements, these derivatives of the original Paxos innovation?
I think so. I think the fact that they're starting to be used in practical systems like Bitcoin, like Ripple, is going to generate enormous amounts of interest. And I think we're going to start to see tremendous innovation. The challenge for systems like Bitcoin and Ripple will be how they'll be able to remain relevant if new systems come up with new innovations that make them better in some dramatic way. Will the existing systems be good enough, or will they be able to adopt those new technologies? It's going to be very, very interesting. I think we're kind of in a similar place to where we were with like search engines, where we knew that search engines were going to be big, but we didn't know if it was going to be like Alta Vista or whether it was going to be Google. You couldn't have predicted which one was going to be the champion because it's a technological battle. It's a battle to provide the best solutions to the real world problems. And that's where we are now. We have all these new systems coming out. They're decentralized. They use distributed databases. They use these same types of principles of consensus, but they differ in many other ways. Systems like Ethereum and systems, all of those, we're going to see all these new systems. And that's going to continue to happen as we have new innovations on the technical side as well. So it's going to be a very interesting time to see what we ultimately wind up using.
Yeah, I did a week of shows on Bitcoin, and what was so fascinating is I found a analogy between like Bitcoin and newer systems versus JavaScript and XML, because like XML, is this like, well, JavaScript is like this kind of the minimum viable language of the internet, and then you had all these things that were kind of maybe contending to try to replace JavaScript. And they kind of lost to JavaScript. And it almost seemed because JavaScript was the minimum viable technology. And then you could make the same argument that like, oh, that's what Bitcoin's going to be. It's going to be the minimum viable technology. I talked to Rusty Russell from Blockstream, and they're building sidechains for Bitcoin. And I look at that and I'm like, that sounds way more complicated, way more difficult than starting from scratch on Ripple. But on the other hand, they've got network effects already. So that's a trade-off for sure.
Yeah, and a lot of Bitcoiners make the argument that Bitcoin is good enough, that for what it's trying to do, Bitcoin is good enough because you can transact in Bitcoins as a currency on other payment systems. People use Ripple to move Bitcoins around all the time. And if you don't particularly care about the payment system, if you care about the currency, then Bitcoin is probably good enough as sort of a digital currency. If you care about the payment system, if you care about making payments fast, then the question is Ripple sort of the minimum viable feature set for a distributed payment network? And I would also point out that these things are not necessarily stuck. Bitcoin can adopt innovations. Ripple can adopt innovations. So it's not necessarily the case. It's still early enough in both of those systems that they could change. So if some new feature turned out to be important, but as we've seen, particularly in Bitcoin recently with the block size fiasco and there is a strong group of people inside any system that has users that don't want it to change. And often for selfish but legitimate reasons, like the miners have invested in mining hardware, and changes that disadvantage the miners they don't want to see. So that makes it very hard to adapt, and that might be ultimately probably. If Bitcoin ultimately collapses and if Ripple ultimately collapses, it will probably because they'll be eclipsed by systems that are technologically superior, and the entrenched interest in those systems make it impossible to adopt those changes. And if you want to look at an example of how to resist that, look at Windows, because Windows really should have been obsolete a long, long time ago because it had to carry forward a lot of craft for compatibility. And yet Windows 10 is like on 75 million desktops now or something, and it still carries that compatibility. So if you want the counterexample to the idea that technological obsolescence but of course, I don't know, will Windows be on our desktop 10 years from now? And if not, what will it take to unseat it? So it's kind of that same sort of model.
Get back to more specificity. Ripple's consensus protocol involves potentially removing bad actors. How does this work?
So you monitor the performance of validators, and we have software that does that now that keeps track of how well they're performing. Essentially, what we're looking for is just poor performance. We're not necessarily looking for malice at the moment. In the future, the types of bad behavior that you might see a sort of arbitrary attempt to enforce policy. Like you might see a validator that says, if you want me to validate your transactions, you're going to have to pay me, some money on the side. You might see governments trying to exert unreasonable control. So you might see the government of a small country saying to validators in that country, you can't validate these particular transactions. Or you just might have too much participation. You don't want like 100,000 validators. It just makes consensus a little bit slower. You just need enough to protect against collusion. And the way bad actors are removed is essentially just by a loose agreement to stop listening to them. And you have sort of like, some people have argued that you sort of need a central authority to guarantee this overlap in the selection of actors, but it's only an authority in the sense that people are willing to listen to them because they do the job better than they could do it themselves. So like if you look at a project like Bitcoin, most people will download the Bitcoin source code unmodified and run it. But right now, there's a dispute going on about what the block size should be, and someone has produced an alternate piece of software that has a different implementation, and people are free to choose which of those they're going to use. So you might have argued that sort of the control over the access to the Bitcoin repository was a central authority that could steer the direction of Bitcoin, but you see, only so long as they make the job easier for people. Like, I don't want to maintain the Bitcoin software myself, I just want to run it. But as soon as there's an actual dispute, as soon as there's some actual disagreement over what that software should do, well, now I'm not just going to run the software that's in the official repository. I'm going to consider these other repositories. I'm going to make these other decisions. So you could have organizations, we sometimes call them attesters, that sort of recommend lists of validators. They basically say, these are a bunch of validators that we see have been performing reliably, and we know what jurisdiction they're in, and we know what organizations operate. But you are free to change what attesters you use, and you use those attesters only so long as they make the decision easier for you. And one of the things that attesters could do is if they see a validator misbehaving, and it's always objectively provable. So let's say a validator refuses to validate a particular transaction over and over. You would see that because they have to sign all of the messages that they send. So malfeasance is always provable. And then an attester could say basically that this validator is not processing transactions fairly, and they could remove them from the list. But we're not really committed to any one particular model of governance. That's going to be up to whoever the eventual stakeholders in the Ripple network are. We think those will eventually be financial institutions. So you might see a consortium of financial institutions similar to what SWIFT has, or I should say perhaps what SWIFT is, that sort of agrees on what validators they want to announce. But it's going to be an interesting thing to see who the stakeholders turn out to be. So right now, the primary stakeholder in the Ripple network is Ripple Labs. And there aren't that many organizations that are interested sufficiently in the governance of the Ripple network to participate. Like there wouldn't be a community disagreement. Like you have the disagreement in Bitcoin, you have enough entrenched interest that there's this big disagreement over the block size. Today, it would be unlikely that you would see that type of disagreement over the Ripple network because there aren't as many interests as firmly entrenched, or at least, But in the future, you might see those same types of issues. One of the other interesting things that Ripple has built in is Ripple has what we call the amendment system, which is a way for someone to say, I want to propose a particular change in the way the Ripple network operates. And they can formally sort of get validators to say they do or don't support that change. And Ripple has a built-in scheme to track when you have a supermajority of validators that support a change. And that starts a 2-week timer, which gives people a chance to analyze the change, argue for or against it, and so on. So we've thought a lot about what the governance of the Ripple network will have to look like in the future, but it may or may not actually look like what we think it's going to look like. It's going to come down to who the stakeholders turn out to be, and it's a little early, really, to know what that's going to be yet.
Why do more servers lead to more security, and what is the trade-off with having too many servers?
Well, more servers lead to more security if they're under different control. Because if you imagine the person who has physical control over the computer could make that computer do something other than we want it to do. And if that computer has some form of cryptographic credential, like a validator would, like a Codius server would, then they could make that cryptographic credential sign things that it shouldn't sign. And so the more servers you have, the more of them you can require to agree in order to do something. So if you have 30 servers, you can require 20 of them to agree for something to happen. And then if those 30 servers are controlled by 30 different institutions, now you have to get 20 different institutions to conspire in order to make that system do something that it wasn't supposed to do. And when you're dealing with something like a smart contract, we're all expecting that funds controlled by the contract will only be dispersed in ways that the contract agrees. We wouldn't expect the contract's key to be stolen and transfer the funds to some arbitrary person who had no participation in the contract. So we want to protect against compromise of the physical machines compromising the assets that the system controls. The downside where you get really, really large is, in some cases, cost. So if this is a personal system that's being used between a small group of people, they're going to have to pay for every system that's going to run this. Like in a smart contract, presumably this hosting is going to cost you based on the scaling. So a very, very large number would be expensive. Now, in a system like Ethereum or Ripple, or Ripple validators, where you're not paying for the individual systems, the disadvantage of having a very, very large number, particularly in Ripple, is the consensus becomes a little bit slower. So essentially, every time you increase the number of validators by a factor of 10, Ripple's consensus takes almost a second longer. So if you go from 100 validators to 1,000 validators, you're looking at about an extra second per consensus round. Now, you could still confirm more transactions per consensus round, so it doesn't so much limit the transaction rate, but it does limit the latency. In other words, the time between when you submit a transaction and when it's confirmed. But also, you really only need enough servers to protect against collusion or compromise. You don't need 1,000 servers run by 1,000 different organizations, because if you're talking about even fairly large amounts of money, someone's not going to compromise 100 distinct institutions to steal your funds. Like having 1,000, there's just diminishing returns. So I would imagine in the future, if we had some very, very large number of Ripple validators, let's say, thousands, that at some point people might just say, let's just pick the ones that are the best in some sense. Let's pick the ones that are performing the best, that are by the most reliable organizations. Let's make sure that we have a couple in each jurisdiction. We don't need 4,000 in the United States, but if we only have 6 in Greece, that maybe we want some more there, because that jurisdictional diversity is another way to protect against collusion. Those types of things would come into play. And it's important to point out that there's no reason anybody needs to run a validator. You don't have to have any special arrangement with a validator in order to process transactions. Just like when you use Bitcoin, as long as mining is working, you don't have to think about it as just an ordinary user. You just have to know that somehow it works. And the same is true in Ripple. There's no special reason that you need to run a validator. And it's kind of funny because sometimes people will tell us, oh, the problem with Ripple is going to be that there's going to be too many validators and the system will break down. And some people will tell us the problem is that nobody's going to want to run a validator. Hopefully the truth is somewhere in between those two, and we'll get a reasonable number. But it's not that difficult to manage.
Well, in any way, you can tweak the percentage of validators that you need, right? So that's kind of a way to ease around that, isn't it?
Yeah, and with a larger number, you can loosen some of the constraints. Yeah, with a smaller number, the constraints are tighter because a single validator, like if you have five validators and one of them fails, you're at 80%, right? Just with a single one. Whereas if you have even if you just have a couple of hundred validators, the behavior of any one single validator doesn't have any significant effect, and that loosens up some of the constraints and makes it a little bit easier. We have a consensus simulator that we use that simulates allows us to simulate things like how many validators do we have? What are the link latencies? How long does it take for traffic to come between the validators? How many transactions are we trying to confirm? And we can test to see what those different topologies do to understand where the safe zones are. What our goal is in that project is to understand where consensus is completely reliable and where consensus is not reliable. Because obviously, if you have completely non-overlapping trust lists that don't intersect at all, then you essentially have two separate networks, and it's not going to work correctly. So the idea is to understand where the danger zones are and then understand what the real network is doing so we're as far away as possible from those danger zones. One of the nice things about Ripple's consensus algorithm is long before that you actually get like a double spend on a live network, way before that happens in simulation, you start to see poor performance. You start to see consensus rounds taking longer. You start to see consensus rounds that fail to reach agreement. So it fails in a soft way. It's not like if the validator topologies got bad, all of a sudden one day we'd have a double spend. That's not the way it happens. What happens is the network starts to perform poorly, and you start to see servers that are not in agreement with the rest of the network, but they know it. And so you can fix those kinds of problems long before they result in real damage.
Can you tell me more about that simulation process, how you implemented that, and what are the themes around how you run experiments with that simulator on a system that's as complex as Ripple, and you can never simulate everything?
That's true. You can't simulate every possible scenario, and it does make some assumptions. So, like, it has assumptions about the distribution of latency of links between the validators. So it will create the number of validators that you tell it to. It'll create the links between them. You can tell it how many links you want and what you want the network diameter to be. In other words, whether you want it to be like really tightly connected or really loosely connected. And then it runs the same consensus logic that the live Ripple servers do. So it goes through the same avalanche process. It goes through the same process of proposing and publishing validations. And then what you can do is you can tweak it by saying, like, I want very small UNLs. I want to trust what if I only have 20% overlap between the UNLs? How does the network behave? And one of the most important things that we get out of it is we get to see, like, as you move from the safe zone to the danger zone, what happens? Like, what fails first? What do those failures look like? So if we ever did see that type of behavior on the live network, we would know what type of problem is likely to be causing it, and that allows us to increase our confidence. The simulation runs fairly quickly because it doesn't do any of the cryptographic operations. For example, because it's completely contained within a single piece of software, nothing is ever invalid, and it doesn't have to actually wait out the latencies. It just goes and does the next thing that's going to happen. So we can run a fairly large number of simulations. We can simulate thousands of ledgers closing. We can simulate all different changes in the topology and get an understanding of how the system behaves in the real world. I wish we had a better theoretical understanding. We're working on that as well, getting a better understanding of what the mathematical bounds are. Like, for example, what do you need to prove that the network can't fail? It's one thing to see that it doesn't fail in a simulation. Having mathematical proofs that particular systems behave in particular ways is nice too. The problem is real-world systems tend to be complex enough and have complex enough failure modes that proofs tend not to apply very well to them.
Right, this is just what I was thinking of. This is just what I was thinking of, because in academia it's like, oh, you just have to work around these Byzantine failures, and we've got a nice little bulleted list of the types of Byzantine failures that you may or may not encounter. And it seems like in Ripple, like in the real world, there's a way, like, it's a combinatorial explosion of Byzantine failures you can encounter.
Yeah, so there's a joke about a mathematician who's trying to prove that a certain racetrack is going to be the fastest racetrack in the world, and he begins his proof with assume spherical horses. We're kind of way behind in what we can prove, and so to cover that gap, we use simulation. It's not quite as good, but you can simulate very, very complex things about which we can't yet form mathematical proofs. And also simulation is nice because simulation allows us to go in the bounds where we know that even if we had a mathematical proof, we can simulate scenarios that don't conform to that mathematical proof to see how they actually fail. And that's very important because we want to design systems that can detect those type of failure conditions and tell you that they're failing rather than erroneously telling you that you can rely on results that it will later tell you didn't actually happen. That we don't want.
So do you have any strategies for how to get closer to that mathematical truth? That sounds like such a difficult problem.
One of the things we've been trying to do is get academics more interested in studying these things. In the early days of Ripple, nobody cared enough about Ripple to study anything. Like, we couldn't get anybody to look at anything because it was like, well, even if you found some horrible flaw in Ripple, nobody would care because nobody knew what Ripple was. We don't have that problem anymore, fortunately. Now that more people know what Ripple is, and Ripple is being talked about seriously for things like settlement between financial institutions, and we have business partners who are, who have test deployments on Ripple. Finding problems in Ripple would be a big deal, so that's good. That means that we're getting more interest. But getting academic interest is a little harder. We've had to work to sort of court people and write sort of like, you could write a paper about this, And if anybody's listening who's interested in distributed systems and interested in looking for things that they could write a paper on or things that could be studied, please, by all means, we're definitely interested if you're working on some kind of a final project or thesis, or there's all kinds of interesting things in distributed systems that work needs to be done on that has immediate practical relevance. And we'll help you in any way. You'll get access to all the technical information we can give you because we need that a lot. That's very important.
I'd like to have a bit of a conversation about Codius. I know you aren't heavily involved in the project. What is Codius?
Codius is a uniform platform for distributing systems for distributing distributed systems. That is, for implementing essentially a smart contract over a number of systems in a way that its operation can be predictable. It's also like, if you wanted to do that without Codius, let's say you wanted to implement a Bitcoin wallet that was distributed over a number of different hosts so that it would operate reliably and you wouldn't have to host it and your credentials would be distributed, you would have to work out agreements with each of several different hosting companies, and you'd have to figure out their diverse systems, and you'd have to write all of the software to coordinate on which transactions to process and when. Codius is a framework for a standardized deployment. So anyone who supported Codius, you could just use a standardized API to buy time on those machines and deploy the contract. And it also has something very much like PBFT that allows all of your instances of the contract to agree among each other. So, for example, let's say you did have a Bitcoin wallet that was a smart contract, and you submitted a request for a payment, and I submitted a request for a payment that you had already approved, and so your contract's obligated to make that payment. They have to agree on which payment to make first, otherwise they could inadvertently double spend. So in other words, if like some of the contract instances see one payment request first and some of the contract instances see another payment request first, they might perform different payments. So you need something like PBFT. You need a consensus protocol between the instances of the smart contract so that the contract itself can agree on what to do. And that's essentially what Codius is. And you need a little bit of plumbing to make that work. You need a sort of virtualization system so that the smart contract can be controlled in what it's allowed to do and what it's not allowed to do. So it's also a virtualization scheme.
So you mentioned earlier that when you're thinking about security with distributed systems, a lot of times you have to be careful and not do too much. But Codius seems like it's fundamentally trying to do everything, and that's not a knock on Codius. It's just that's what it does. Is my impression. So maybe you could address that and describe some of the security principles around a smart contract platform.
That's a fair criticism. We definitely did bite off a lot, possibly much more than we could chew, and also it's kind of a little early because some of the use cases aren't really there. The basic way the security works, so the virtualization is the standard virtualization solution. Originally, we were using Google's native client, which is the same virtualization that they're developing for browsers to be able to run native software in a virtual machine. On the cryptographic side, well, the contract can recognize the other instances of the contract because they're sort of deployed as a unit. But The problem is exactly what you point out. Like I could sort of give you a short, simple, bulleted list of all the things that you have to do to make this work, and it seems like, oh yeah, there's just 6 or 7 things, and I see how you would do each of those things. The real world is not that simple, and it's largely because of the security problem that these things have to be secure, and that makes development very, very slow and very, very painful. And I think to an extent we did bite off perhaps more than we could chew, and it's kind of unfortunate because it was a very exciting and interesting idea, but how long before you're going to see it actually deployed and useful? I don't know.
So I don't know if can you talk about Ethereum? Or are you comfortable talking about Ethereum?
Sure.
So I mean, how does that compare to Ethereum? Because Ethereum is doing something very similar, and presumably they encounter the same sorts of security issues. Is there anything that they're doing that would alleviate the same types of concerns you have around Codius?
So they're trying to do essentially this, to some extent, the same thing that Codius is trying to do, but they have a very, very different approach. And their approach is pretty clever. So the way Ethereum works is that a miner that wants to mine sort of a smart contract to get the transaction fee has to run that smart contract and include the results in a block. And then other servers, just like on Bitcoin, verify the results of that. The problem with Ethereum, largely, if you're imagining it trying to tackle the same types of use cases that Codius is trying to address, is twofold. Number one, it's very hard for an Ethereum contract to protect a cryptographic credential. So what has to happen in an Ethereum contract is the fact that the contract was mined has to trigger something to happen. It's a little bit more difficult to do than, for example, a Codius contract that could execute a Ripple transaction or execute a Bitcoin transaction. They're not quite as active. But as long as someone has an interest in the result, then you presume that the person like if we have an Ethereum contract that decides whether you or I get something, presumably if you get the money, you have an incentive to make sure that that transaction actually happens. But the other problem is scalability. Essentially, every miner that's going to mine the Ethereum contract has to run that contract, and you have no control over who runs it. So you don't have there's no private contract data. And there's no sort of horizontal scalability where you could have thousands of hosts all running completely different contracts. So they're aimed at fairly different use cases.
And how do those two, Ethereum and Codius, how do those compare to the scheme of Bitcoin with sidechains, which would presumably extend the functionality of Bitcoin?
Yeah, so what sidechains allow you to do in Bitcoin is two things. Number one, they give you horizontal scalability. So if you have Bitcoin and you have some number of sidechains, you can now process more transactions because each sidechain has some number of transactions that it can process. So they give you that sort of immediate horizontal scalability, which is good. That's definitely something that Bitcoin needs. And the other thing that they give you is that each sidechain can have its own rules that only have to be agreed upon by the people who use that sidechain. So if that sidechain could have a higher block, if it's a traditional blockchain, it can have a faster block time. The problem with sidechains is if those sidechains are going to use proof of work, then how do you pay the miners on the sidechain? Like, what do you pay them out of? Whereas if those sidechains are sort of run by a central authority, then Bitcoin with sidechains is really nothing different than a system like Coinbase or something that just has a central repository of balances. So it's definitely very interesting, but the use cases are somewhat different. I think if you want horizontal scalability of Bitcoin, if you just want to be able to perform lots and lots of Bitcoin transactions, the solution is to use some system that has whatever characteristics you want to move Bitcoins around, whether that's a proprietary system or even like people use Ripple to move Bitcoins all the time. You could imagine sidechains that have Ethereum-like properties that support smart contracts. And that way you could use because a sidechain can have whatever rules the people who use the sidechain want. A sidechain could be an Ethereum-like chain. And there are definitely people who are looking at building Ethereum-like chains as Bitcoin sidechains to get those additional features. It's going to be very interesting to see how this all shakes out. The big question, though, is what are the use cases for smart contracts? Like most of the use cases that we talk about for smart contracts are fairly theoretical or fairly narrow. And that could just be a lack of vision on our part. I'm certainly not going to say that there's nothing that they're good for. It's kind of like people talking about, what would email be good for in the 80s? We say, well, why do people write letters to each other? Well, that's what email would be good for. But we're certainly wrong about that. So we don't know what those use cases are yet.
Okay, well, let's talk about the most absurd and ambitious use case. And this is sort of the ultimate security question. So Elon Musk and Stephen Hawking have been talking about the dangers of AI. And I was talking to Melanie Swan, who writes a lot about blockchain stuff, and she said that you could have a smart contract system that would be a safe platform for a friendly AI to develop. And so I'm just curious if you agree with this, and maybe you could explain some hypothetical scenario of how you could develop a friendly AI on this sort of platform and why it would be safer than traditional compute platforms.
So we do already see bots on Ripple that do things like fight for the tip of order books. They're fighting to offer the best liquidity rates to get to make a profit. We don't yet have systems that sort of pay their own way, where their existence could be threatened. So, for example, you don't see Ripple bots that pay for their own hosting yet. You could in the future, though, and certainly through smart contracts. But one of the nice things about these systems, like if you're worried about like the ultimate doomsday scenario, and I understand why you would feel that way, because these are systems that are sort of close to finance, right? They have access to money, they're automated, and they don't really have an off switch. Like there's no Bitcoin off switch, there's no Ripple off switch. So I'm sympathetic to the fears a little bit, but I will point out that we do have the ultimate off switch. Like if some robotic system took over Bitcoin or Ripple in such a way that it posed a real threat, we could just stop using that platform, right? Like we could just like if we all agreed, we could just stop using Bitcoin and switch over to something else. All it would take is the majority of people to create a new blockchain that had their Bitcoins on them, but not, this AI. So they're safe in the sense that they're on systems that we could ultimately abandon if we absolutely had to. In principle, we could even sort of get together and delete specific things out of those systems. We retain ultimate physical control over the systems. Notionally, you could imagine an AI that could like hop from system to system. I mean, if you get into the crazy movie plot scenarios, but we could just shut down whatever protocol it was using. I mean, in the worst imaginable scenario, we could just abandon that protocol and replace it with another one. So I don't think we have to. I think they're safe in the sense that they're not going to be able to evade us forever. Really, the more dangerous platform is the internet at large, because if you imagine, you have a lot of Windows PCs that are very, very homogeneous. They're very similar. They have many of the same security vulnerabilities. They have communication. They have access to the World Wide Web, so they can make payments. They can control anything that's reachable via the web, which is essentially everything. They can send out emails to people promising them Bitcoins if they do specific things. So you could sort of imagine that kind of nightmare scenario. But we're a very, very, very long way from an AI that had any of those kinds of capabilities. But definitely people should continue to think about those kinds of things because we do want to make sure. I mean, I like I said, even if we tried, even if we did everything wrong, I don't think we could have that kind of a nightmare scenario for 50 years at the absolute minimum, probably longer. But definitely we should keep those things in mind and make sure that we do have controls in these systems. But it is a fear. But I would argue that it's not necessarily new to these platforms. It's really the internet at large that's more dangerous. And these platforms are safer because we could abandon them, whereas abandoning all Windows PCs would seem like, kind of an unthinkable, it would be much more painful rather than just like switching to a new Bitcoin blockchain in which these things were deleted. It's certainly safer in that regard.
Is there anything else you'd like to add about Ripple?
I'd like to add one thing about Ripple Labs, which is that we're always looking for talented people. We're always hiring. And if there's anybody associated with a financial institution who's listening, that we're always looking for partners. And we offer a new way to settle that's faster and that provides certainty very, very quickly. And it was a pleasure talking to you today, Jeff.